So this is a lot like what we talked about before when we had, before we did the fundamental theorem of calculus, we were able to do lower and upper sums, and that's really what they're talking about here. But you're going to come across functions that you can't do the antiderivative of, at least not yet. We don't have the skills. So they're falling back to, okay, do this upper and lower sum, or, if it's a decreasing function, your left bound is just decreasing, left is going to be the upper and right's the lower. If it's an increasing, then your right is the upper and left is the lower. We do it, your right's upper, left's the lower. And so you can bound it, they call it bounding the actual value. I'm sure we used that terminology back then and doing that. So like here's an example of if you were to take the derivative, but we're not going to take the derivative of that. They just used a computer program to do it anyway. So that's pretty messy. But integrating something like that could be really, really hard. Another example, this is a real popular example right here, is g of x equals 1 over the square root of 2 pi e to the negative 1/2 x squared. So this function is not something, you don't need to write it down. It's not something you're going to deal with, at least not now. Someday you may deal with it, especially if you go in statistics and take calculus-based statistics. It's used there quite a bit. But this is an example of a function that you can't integrate it. Why can't you integrate it? Because if you made u the negative 1/2 x squared, there's no du. So we can't do anything with that. So instead, we can have computers come up with the area. Now you're asking yourself, why is he showing this to me? And why is it even in the book? It's because it's a very popular formula that comes up that models this normal distribution, and especially as seen. So there's something called the normal curve, and that's a general population tends to fit into a normal curve. And you can estimate what part of the population you're dealing with based off of what how many standard deviations you are going out from the middle. The middle is the mean, and you go out so many standard deviations. There used to be people thought, when I was in school, as a student, I think I'd already taken calculus, but I was in actually a calculus-based stats class, and we were talking about this, but people would think, oh, 3 standard deviations is the most it goes out. It actually goes out forever. That curve goes out forever. There's a real popular usage of this curve, especially in like social sciences. You know what it is? For measuring IQs or to scale where IQs might be. And so I've heard different numbers more recently, but it typically was your average IQ was 100 and it goes up, 1 standard deviation was 15. So 115 is, well, the first standard deviation. If you looked at within 1 standard deviation, so from 85 IQ, you can actually do from your perspective, from 85 to 115 captured, I think 68% of the population. 2 standard deviations, I think it was like 97.5% of the population. So going from the low end of, it would be 70 up to 130 is like 97.5% of the population. I can get the numbers if you care. And then if you go up 3 standard deviations, you're at like 99.8% of the population, something like that. So those curves really start coming down towards the endpoints as you further out you go. So you're capturing less and less population because you've already captured the majority of it. And that's significant because 3 standard deviations counts for, that's Mensa, that's genius. And so to qualify, you have to take usually an IQ test in the fall there. And sometimes people get phone calls if they were like college placement exams, they can qualify you as well. So, and all that does is says how quickly you are able to evaluate or solve a problem compared to the standard population. There was a singer named Prince. You guys have heard of the singer named Prince? Okay, why? You never know. So there's a singer named Prince back in the 80s and 90s, and he was supposed to be like way off the chart, like 180 IQ. So it's around 145 is the genius level, and he was like 180. He's way up there. So from your perspective, he's way up there. Typically, when people get up there, they tend to lose some other skills. It's like some social skills. It's not a criticism. It's just a reality. I have a cousin who's I don't think he's actually a member of Mensa, and he could be though. But he connects with people, but that could be a challenge sometimes. He's really smart. Anyway, and there's another person I know. I won't go into it. That typically turn this off. I don't know what's on. Some Mensa people will tell you when they're in Mensa. Okay, we'll leave it at that. So I'm not in Mensa. Don't worry about it. So this is just an example of looking at the area under the curve, and like we did before, break it up into intervals. You have the upper estimation, you have the lower estimation. This one is a decreasing function. The left-hand interval is going to give you the upper estimation, and likewise, in this type of case, the right hand is going to be the lower estimation of it. So here's a picture of it down here. So again, I still ponder why was this thrown in here, but I want to look at an example from the book, from the homework that they had. So I'm going to do that here. This is yours might be exactly like this. It might be slightly different. And it says simply like 8.7 is less than or equal to the integral from a to b of f of x dx less than or equal to 9.8. So it says with a midpoint estimate, come up with the maximum error possible. So what this is saying, the area under the curve is 8.7, area under the curve is 9.8. So on the high end, it's a 9.8, on the low end, it's an 8.7. So if you said that the actual thing is the midpoint, what's the maximum area going to be? And this is as simply as this. You're going to think that you're going to feel insulted how easy this is. 9.8 plus 8.7 divided by 2, and I got 9.25. Then you take that 9.25, you say, okay, the high value minus 9.25 is 0.55. 9.25 minus the low value of 8.7 is also 0.55. So the maximum error is 0.55. That's it. There's a couple of problems like that you're going to do. I have another one I'll show you.
What number was that?
I think that was like number 1 from the homework. I was just frustrated that the book didn't actually give you any good examples. There are then also the examples where you're going to then do a lower estimate and upper estimate, which I figured you're already good at. You already did those several times when we did Riemann sums and before that. So I have another one for you, and it says 1/12. Again, this could be exactly like yours. Yours could be slightly different. Is less than or equal to the integral from a to b of f of x dx, less than or equal to 1/5. So again, that means 1/12 is the area under the curve on the low end, 1/5 is on the high end. And so what's the maximum error? You find the middle point and subtract either endpoint. It should be the same if it's a middle point. So the toughest part here is dealing with fractions. So if we took the 1/12 plus the 1/5 and divide by 2, that's like saying, I multiply this by 5/5 and this by 12/12. And I end up with 5/60 plus 12/60 divided by 2. That's going to be 17/60. And divided by 2 is like multiplying by 1/2. So it's going to be 17/120. That's your middle value. So you take that 17/120 and subtract 1/12 from it. Well, that's easy enough to do. Multiply that by 10/10. So 17/120 minus 10 over 120 gives you 7 over 120. So there's the error. Likewise, 17 over 120 minus 1/5. Multiply that by what? 5 times, I think it's 24. 24 over 24. So it's 17, I should say absolute value here. 17 over 120 minus 24 over 120 gives us negative 7 over 120, absolute value. So it's going to be 7 over 120. So the maximum error you're going to have for this one is at 7 over 120. So that's a couple of the problems. I think there are only a maximum of 6 problems in this section. So that's the first 2 are like that. And the others are going to, you're going to estimate the sum, the upper and lower bounds, upper and lower sums. And those are the bounds. I just didn't want to throw you off on that because I felt like we were finished with that. And here we are coming back to it.